Hello everyone, and welcome to today's webinar. My name is Sahar Paksaj, and I'm the Marketing and Communications Coordinator at Clone Krippenberger. Today's speaker is Harvey McLeod, KCB's Vice President, Strategic Marketing, and one of our senior geotechnical engineers. He will talk about challenges with upstream tailings dams, which is a presentation he recently gave at the ICOLD conference in Ottawa. If you have any questions during the webinar, please enter them in the questions box in the GoToWebinar panel on your screen. Also, a copy of today's presentation is available to download from the handouts section. An on-demand recording of this webinar will be available on our website at clone.com. You will get an email about it as well. So as I mentioned, today's presenter is Harvey McLeod. Harvey is a geotechnical engineer with 45 years of experience in all aspects of tailings dams. He has worked on hundreds of tailings dams in all types of conditions in over 30 countries. He has been active with ICOLD for 20 years and is currently chair of the subcommittee on tailings dams. Harvey also helped the BC Ministry of Energy and Mines with the investigation into the Mount Polley tailings dam failure. Welcome, Harvey.
Thank you very much, Sahar, and good afternoon, ladies and gentlemen and fellow colleagues. So my talk today is going to focus on the challenges of upstream tailing dams. As you're well aware, with the recent failure of Brumadinho in Brazil was a very tragic and catastrophic event. And the photos that you see on the top left there is the initiation of the failure, which looks like it bulged out at the toe. And seconds later, the whole dam went, and you can see it in full failure mode. And then in the bottom right there, you can see this is a video that was captured just downstream of the dam with a camera located on a conveyor. And the material is basically flowing like a thick fluid. Now, why was this so tragic? Why was it so catastrophic? Iron ore slime tailings do have some particular characteristics, and I'll get back to that during my talk. But it's a grim reminder of what can happen with these upstream tailings dams if we're not understanding the mechanisms that are involved and what can happen with such failures. Now, my talk today is going to cover generally, what are upstream dams? How are they constructed, with some examples around the world of different ways of building upstream dams. Secondly, it's the tailings properties. What are the differences between different kinds of tailings, and what is their sensitivity to static flow liquefaction? Thirdly, I'll give some examples of case histories of static liquefaction and consequences of failure, and discuss when a dam breaks or fails, how can it behave? And lastly, it's challenges with assessing the safety of upstream dams. Upstream dams are fairly complex structures, and there are challenges in just the design and analysis of such dams. Now, what makes upstream dams different? First of all, I guess, is a very simple case. The figure on the bottom left there shows a typical upstream dam, which is generally start with a starter dam, and then it's raised during the life of mine, usually with little berms on the outside crest of the dam, with tailings spigoted upstream. But you'll see also there's a dashed red line that I put in here, and that is that zone and downstream is essentially the structural zone of the dam. So if this was an earth-fill dam, that would be your part of your earth-fill dam. And I think it's the appreciation that this section here is really a dam, and we have to treat it as a dam and analyze it as such. Now, there are thousands of upstream dams constructed around the world, and not all of them fail, obviously. And they have advantages. So I've got a list here of the advantages of upstream dams. They are less cost. So basically the structural zone is constructed out of spigoted tailings as opposed to boro material, which needs to be extracted and compacted in place, which costs more money. Also, there's disturbance of ore material if you're taking material from downstream of the dam. They can also be progressively reclaimed so that the lower slopes can be reclaimed as you're raising the dam. But the disadvantages of upstream dams, there's very limited quality control over placement of the tailings. Basically, they're being placed as an inhomogeneous zone with a lot of variability, and that has to be taken into account. During the life of the mine, you can have changes in ore types, different mineralogy, different types of tailings, different spigot locations, which may lead to sandier zones and finer zones within the structural area. Different climate conditions, different efficiency of thickening, drying times, etc. And the other component is loose tailings, when saturated. They're susceptible to liquefaction. They are contractant. They're not compacted, and under certain conditions, they can liquefy. Now here are just some examples of types of upstream tailing dams. The bottom figure there illustrates, you can see the typical section of a starter dam and raises showing in the green. And this figure here has different tailings zone 1, tailings zone 2, tailings zone 3. And the idea is there you're spigoting the tailings and they're segregating along the beach with a coarser zone on the exterior of the structure and gradually finer as you move into the interior. So this helps reduce the phreatic surface in the dam and improves the stability. I think in this case, the phreatic surface is pretty well along the contact between tailings 1 and tailings 2. And the other approach, and in the mid-60s, I guess, the use of cyclones to segregate sand from tailings was developed. Initially, it was used here in British Columbia with Earl Clone with design of centerline cyclone sand dams. At about the same time, predecessors to Knight and Peasold were using cyclones to produce sand to promote drainage on the outer slopes. And these are just some photographs in the top of cyclones on an upstream tailings dam being used to create a wider drained zone of sand. The other approach that gets taken is desiccation, taking advantage of drying, particularly in arid climates. And in South Africa, one example, the procedure is called day wall construction, where a zone around the outer side is constructed out of tailings which are placed in a cell and then allowed to dry. And this creates freeboard. It also creates a stronger outer zone. And it is interesting to note, and when we talk about tailing properties, some of the tailings that do come from smelter slimes have very unusual properties. You can walk around the outside of some of these dams and hit the tailings with a rock hammer, and it's almost like cement. So we have some quite different properties, and trying to analyze these structures is very interesting. Another approach, and this is with the mud farming with the bauxite tailings in Australia, and they're using what's called an amphiroll. It's basically a piece of equipment that goes around the top of the tailings, churning them up and exposing them to drying, which reduces the water content. There are some challenges with this in that during the rainy season, tailings can get re-wetted. And also as the dam is raised, the consolidation of tailings can resaturate the zones that previously had a lower water content. This is another example of the benefits of desiccation. This particular dam ended up developing zones that progressively went from the outer embankment, the light green, moving towards the interior of the impoundment. And in this case, let's say tailing zone C and B and A. Now C on the outer side, which was closer to the deposition and had more desiccation, it has undrained or peak undrained shear strength ratios of 0.6, which is almost approaching a drain strength. And as you progressively move in, you go to 0.4 undrained shear strength ratios until you're in tailings A, which is basically normal tailings at about 0.23. So here you've got the advantage of a stronger outer zone. Now there is still some uncertainty with this though. I mean, the behavior of the desiccated tailings and its brittleness is some uncertainty. If it's stressed, does that brittleness break, or the bonds break, and does the strength reduce? Nonetheless, those illustrate that there are many ways to build upstream tailing dams. The next one is one of my favorite ones. It's mine in Sudbury, and this is what we call a hard rock tailings, good competent tailings. And there, they spigot tailings out on the beach, and it's hard to see, but there are spigot points all along the crest of the beach there where the trucks are. And a dozer is running back and forth compacting it. So even though this is called an upstream tailings dam, in effect, it's a constructed compacted embankment. And in this case, the tailings are just spigoted whole. They're not thickened, and you're able to get the compaction. Now, my next, this slide here is an illustration that we have been in ICOL developing a bulletin, and it's being published as we speak, called Tailing Dam Technology Update. And one of the key chapters in the bulletin is tailings properties. And we have classified tailings in 5 categories, going from coarse tailings, which is basically a non-plastic silty sand, to hard rock tailings, to altered rock tailings, and that would be where you're starting to get some clays and some plasticity into your tailings, to fine tailings and ultrafine tailings, which is basically high plastic silty clay. So you have this continuum of tailings, and so when people refer to tailings as a single product, it's quite variable. And even in one tailings pond, you can have different types of tailings due to segregation and different deposition methods of the tailings. Now, in the ICOL bulletin, we have developed for each of these types of tailings a number of charts that relate the coefficient of consolidation, charts that show consolidation curves, void ratio versus stress, a chart showing yield stress of tailings plotted against both void ratio and percent solids by weight, and also permeability. So with these classifications, you can start to get an appreciation for the type of tailings you have and the behavior. And there is a very simple test to get an initial indication of the type of tailings that you have. This is, I've got at the bottom here, I call it a simple jar test. And this is a test where I just went out onto a tailings beach, picked up a handful of dry tailings, took it back to the laboratory, and mixed it to 50% solids by weight and put it in a beaker. Now, typically, tailings would take sort of 2 hours to 2 days to settle, and you can see in the photo there, this is coal fines. The tailings have settled, and in this case, they settled in about 2 hours. And then you can calculate the settle density, percent solids by weight, and you go to the chart, which is in the ICOL bulletin, solids concentration on the left, settling time on the right, and that particular tailings plots basically as a coarse tailings. So with a very simple field test with minimal lab work, you can get an appreciation of the potential properties of your tailings. The next main concept, and it's kind of going back into basic soil mechanics, and to illustrate it, I've got the schematic on the right there, and you can kind of imagine it's a card-like structure, and I credit Dr. Peter Robertson for this reference. But the schematic on the left there, the cards or the spacing is wider apart than on the right. And you can imagine if you put a horizontal force to the top of this, this particular structure would collapse faster than this structure. And it's a bit like the tailings in an upstream tailings dam. They're sitting there basically in a what we call a contractant state. If it's stressed, it'll start to collapse, and the denser it gets, the more resistant it is. So we have referred to as the critical state line, the void ratio versus mean effective stress. If the void ratio is higher than the critical state line, then it's behaving as a contractant material subject to collapse. And if it's below the critical state line with a higher void ratio, as it shears, material tends to open up and pore pressures decrease. Now, the susceptibility to liquefaction is linked, if you like, to the basic properties of the tailings. That's important because the plasticity chart is still a very valuable tool. As Carl, the Swedish Carl Atterberg, the Atterberg limits in the early 1900s, came up with this plasticity chart. And as you go up the A line here, you get higher void ratios and more plastic material. But the other important component of this is not just the plasticity, but also what's referred to as the liquidity index. Basically, the moisture content minus the plastic limit divided by the plasticity index. And this, it was noted by Carl Terzaghi in his 1948 textbook that if the liquidity index is over 1, the material tends to flow. Now, if we look at the Fundau slime tailings, and if you take into the data as to what was the liquidity index of the slimes, not the sand, but these are the slime tailings, it had a liquidity index of 2. And plotted here on this chart, this kind of red circle, and this is an area where the liquidity index is in the order of 1.5 to 2. And certainly if you're in this zone, and also if you're even below here, this area is more susceptible to liquefaction and to flow. As you go below the A line, the liquidity index decreases. And as you move up the A line to more plastic tailings, the liquidity index actually decreases. So we have in the industry, we've always talked about fines correction for CPTs and SPTs. And I think we should be thinking not necessarily fines correction, which we've always been suspicious of, but it may be a plasticity correction. As you move to a more plastic material, when the structure is deformed, the bonds do not break as easily, and it behaves more ductile. The other knowledge we can get is from the CPT, and certainly the CPT is the best technology these days for getting spatial data of the tailings. You can drive many cones quickly, get continuous readings. This is a plot, it's typical hard rock tailings plot, and you can see it's highly variable. It's a plot of normalized cone resistance versus the friction ratio. And basically this, everything below this line here is dilative, and everything below is contractive. So certainly in this case, most of the tailings are contractive. But if you plot, again, go to the Fundau data and dig out where the slime data plotted, you can see there are a couple of points right at the very low end here. And this whole area is classified as contractant clay sensitive by Dr. Robertson. But you can see these values are quite a bit below even some of the other curves and data that we have. So certainly getting CPT data that's plotting in this region and getting liquidity indices, which are on the order of 2, are indicators that the tailings could be more susceptible to flow liquefaction. Now, what happens when a dam breaks, when it's stressed and fails? Do they fail like Brumadinho, or what are the different mechanisms? So the two at the bottom there, the most recent one, Cadia on the left there, basically it's a hard rock tailings. The water pond was away from the dam. They noticed a crack in the morning and evacuated downstream, and it failed later that day, but it basically deformed from approximately 4 horizontal to 1 vertical slope to about 7 horizontal to 1 vertical slope. And that's actually quite similar to the Sullivan mine failure in Canada in the 1990s. This particular structure, it was Friday afternoon, the last lift going on the dam for the construction season. And the grader operator had to start adjusting his blade because, although he wasn't aware of it at the time, the dam was failing. And a pickup truck near the toe of the dam, it appeared that the liquefaction started near the toe of the dam with progressive failure. The fellow in the pickup truck, the fine sand and gravel in the foundation liquefied and flowed into the pickup truck, and he had to climb out the window. But this structure, it failed and deformed from, again, about a 4 horizontal to 1 slope to about 7 to 1 slope. Now, the recent failure in Mount Poly, in that case, the flow, the dam break, was primarily driven by the water. They had storage of something like 10 million cubic meters of tailings, and during the failure, which occurred over a period of hours, about 10 million cubic meters of tailings were washed away. But you can see in the photo there that the residual slopes, they're about 2 horizontal to 1 vertical. So we didn't get liquefaction of the tailings. You certainly had mud flow of saturated tailings and going downstream, but we did not get full-scale static liquefaction of the tailings as we did in Brumadinho or even in these other 2 cases. And then in the top left, that's coal and tar in Hungary. There you did get quite a flow of tailings, and you can see these residual slopes in the back are probably more like 10 to 1. So you are getting likely static liquefaction and flow there in addition to what the water was transporting. So when we're thinking of dam break assessments, we do have to be thinking of the key mechanisms. Your prime mechanism is certainly water. The more water you have in the tailings pond, when it breaks, that water will transport tailings. And a rule of thumb that I've been using for a number of years is that if you have a cubic meter of tailings, it can wash a cubic meter of, if you have a cubic meter of water, it can wash a cubic meter of tailings. So limiting the quantity of water that you can have in your tailings pond is important. And in assessing your extreme consequences, it's looking at, in extreme flood conditions, how much water can I get in the impoundment? And the secondary mechanism is the static liquefaction. Is the tailings you're dealing with sensitive to static liquefaction? Is it going to behave like Fundão and Brumadinho? Or will it behave more like Cadia and Mount Poly? And you need to assess each structure and assess the susceptibility to flow liquefaction and flow. The other component we have to think here is that for seismic conditions, I mean, all tailings, well, virtually all tailings, are loose, and when saturated and subject to sufficient seismic loads, they will liquefy. So with the seismic conditions, you're looking at widespread liquefaction of tailings within the structure and the run out of the liquefied tailings. And I do put in the last is tertiary mechanism, which is what I call just localized mud flow of saturated tailings. So even though the water will transport a lot of tailings downstream, you're going to get some residual mud flows around the tailings facility, which are difficult to predict. Now, my next few slides, they deal with some of the issues of assessing upstream tailing dams. And one common issue we've had is understanding, well, what is the seismic response of the tailings to seismic loading? And the other component is what we call static bias, which accounts for the stresses that are in the sloping dam. So the figure on the left shows expected acceleration of for a typical project with a period on the bottom. And tailing dams, which are, say, in the order of 20 to 40 meters high, they have a spectral period of around 0.3 seconds. Higher dams, if you're 100 meters high, it's more like a second. And this is a bit like in the building industry, where your 3-story buildings are more susceptible to seismic damage than your high buildings because of the period of the structure. But in this case here, on the right, we have a project where we have factors of safety against liquefaction. And without accounting for any amplification, for example, here we have a factor of safety of around 1.4 at this point. But with amplification, that takes your acceleration from 0.12 g to, say, 0.2 g. Your factor of safety reduces to about 0.8, which is a significant reduction in your factor of safety against liquefaction. The other component, I mentioned the static bias. If you account for a static bias in this particular example, you go from 1.4 to about 1.2, so about a 15% reduction in the factor of safety against liquefaction. And so in this particular case, accounting those for both the amplification and the static bias, you go from a factor of safety of 1.4 to 0.7, which is like 100% or 50% reduction in the factor of safety, and basically a higher susceptibility to seismic liquefaction. The next challenge that we have with the upstream tailing dams is the interpretation of what are the properties of the tailings. I've mentioned that it's a heterogeneous product, the tailings, and it's important, particularly with CPT testing, to understand what it's teaching us and what is reasonable to learn from the SPT data, CPT data. Certainly on the left here is the pore pressure response. And it's the pore pressure conditions within a structure can be quite complicated sometimes. It's important to understand, well, first of all, if you are getting a pore pressure response, it's indicating you're getting contracting behavior. And then when you get your equilibrium condition, just assessing just what is my equilibrium pore pressure conditions within the structure. The second figure there shows the undrain strength ratio, SU over sigma V. And then you can see it varies considerably as you drive the cone from like 0.1 to 1. And the practice in some places is to take the median value and use that as the strength of the material. I think which I don't believe is appropriate. And using the absolute lowest value may not be appropriate either. So interpretation is very challenging. And we talked about using the lower quartile, which some people use. The other option is using the median value, which I believe is not appropriate in that you've got a very variable material, and certainly it likes to fail on the weakest layer. The other aspect is what I call micro-interpretation of layers. This is an example where someone had interpreted the CPT data and come up with something like 10 or 12 different layers of tailings. And I think the reality is with the variability and distribution of tailings and properties, believing that we can actually analyze or interpret discrete layers within the tailings is unrealistic. So my last comment on challenges with upstream tailing dams is in the analysis. The limit equilibrium analysis is basically average factor of safety along the failure surface. And it doesn't always indicate where you may have stress concentrations. This is a particular example where we modeled it flak analysis, plotting out here the factors of safety, and the red zones here are where the factor of safety is less than 1. So you have to be cognizant that the zones of low factors of safety can initiate failure and lead to progressive failure of the structure. And so the challenge to confidently predict the soil behavior in the stress state is difficult. We get undisturbed samples in the field, which require the use of thin-walled samplers and very careful sampling, transport, X-ray of tubes to assess whether we're getting any disturbance, and then we carry out laboratory tests under very controlled conditions, and they do help to inform us about the properties of the material and how it may behave when stressed. But we do have to recognize the limitations of taking a single sample from a very heterogeneous deposit, and how many samples do you need. But they do help to build up a body of evidence that can inform how the soil might behave and can inform your flak analysis and stress state and the changes both under static and dynamic loading. And I think that considered with the CPT data, basically have what I call a body of evidence, where you're getting the evidence that gives you the information to inform you as to the safety of the structure and what parameters you should be using. And it's not a single one of these, but it's all of these together and account for the uncertainty with the materials and the uncertainties of sampling, uncertainties of testing, to come up with the assessment of the factor of safety. So in summary, upstream tailing dams have a long history in the mining industry, and there are thousands around the world. Are they all unsafe? No, but the actual factor of safety is less than we think. Typically, if you have a 3-to-1 slope and the static factors, drained factor of safety of 1.3 to 1.5, your undrained strength factor of safety is probably close to 1. The triggers for static liquefaction are difficult to predict. Uncertainty in material properties, uncertainty in stress state, and I haven't talked about triggers for static liquefaction, but even understanding what can trigger static liquefaction and the accuracy with which you can predict that and the uncertainty is a challenge that we face. A factor of safety of greater than 1.5 for peak static undrained shear strength may be adequate, however, not in all cases, and has to be considered on a case-by-case basis and on the tailings properties, amongst other things. Now, the preventative practice is to assume liquefaction could occur and adopt a post-seismic condition. But I do have to discuss, even when we talk about the post-seismic condition, what is the post-liquefaction undrained shear strength. In one of the earlier slides with the CPT data, for example, your post-liquefaction undrained shear strength can vary from like 0.12 down to 0.05 or even lower for the case of Fundau. And the difference between undrained shear strengths determined from correlations with the CPT as opposed to undrained shear strength from case histories are different. So understanding just what your post-liquefaction strength could be is important. But safe design of upstream dams, it is possible. We need to understand the type of tailings and its properties. We need to understand the undrained response of contractant tailings. and more importantly, recognize the inhomogeneity of the tailings and the uncertainties of the assessment by recognizing the variability and challenges of the actual conditions. And I have in bold in brackets again, but it's assuming parameters that account for the uncertainties, and we cannot be too clever about any of the methods that we use when dealing with upstream tailing dams. Thank you very much.